Hello everyone, welcome back to my video lecture series on Introduction to the Finite Element Method in 1D. So in one of our previous lectures, we discretized the weak form, and using that we generated a system of equations or a matrix equation given by KD is equal to F. Here K is our stiffness matrix, F is the forcing vector, and D is our unknown solution vector which we need to solve for. So in today's lecture, we are going to discuss how to evaluate the stiffness matrix and the forcing vector now that we know what the basis functions are for the linear finite element method. So let's start by writing out what the stiffness matrix looks like. So the stiffness matrix KAB is given by A of NA, NB, where NA and NB are our basis functions, and this can further be written out as integral over the domain from 0 to 1 of dNA by dx multiplied by dNB by dx, whereas the forcing vector FA is given by NA, F plus NA of 0 multiplied by H minus A of NA, NN plus 1 multiplied by G. Here H was the constant for our Neumann boundary condition, whereas G was the constant for our Dirichlet boundary condition. This can further be expanded as integral 0 to 1 NA multiplied by F dx plus delta A1 times H minus integral 0 to 1 dNA by dx multiplied by dNn plus 1 by dx into G. Now how did I get this particular relation over here? So NA of 0 times H can also be written as NA of x1 times H, because our first node x1 is nothing but 0, which can now be simplified as delta A1 times H using the relation NA of xb is equal to delta AB. So that's how we get this particular expression over here. So now let's see how we can evaluate the stiffness matrix. So KAB, which is given by integral over the entire domain 0 to 1 of dNA by dx multiplied by dNB by dx. Now in the finite element method, instead of evaluating the stiffness matrix over the entire domain, we instead evaluate it over each particular element and then sum up the contributions of all of the elements to the stiffness matrix. So essentially what that means is that KAB can be written as summation over all elements E equal to 1 all the way up to element number n of integral over each particular element's domain omega E dNA by dx dNB by dx, which can simply be written as summation E equal to 1 to n KAB E. Here KABE is basically the contribution of element E to the global stiffness matrix K and can be defined as integral over the domain of particular element E dNA by dx dNB by dx. Now let's remember what element E looks like. So if you remember, element E includes two nodes, node xe and node xe plus 1. Within element E, only two basis functions are non-zero, and they can be expressed as follows. So you have basis function ne, which is centered at node ne xe, and you have another basis function ne plus 1, which is centered at node xe plus 1. So since only two basis functions are non-zero within element E, if you go back to this expression, then this integral over here is going to be 0 for pretty much all values of A and B. The only cases where KABE will be non-zero are when A is either equal to E or E plus 1 and B is equal to E or E plus 1. So only when A is either E or E plus 1 and B is either B, E or E plus 1, both the first term and the second term will be non-zero since those two basis functions are active, and only in that case the integral will be non-zero. For all other values of A and B, this term is going to be 0 because at least one of these two terms will be 0. So if you try to look at this particular matrix KE and try to see what it looks like, then KE will look like follows. So in general, it is an n by n matrix, but most of the elements in this matrix will actually be 0. The only non-zero elements of this generally n by n matrix are the column numbers E and E plus 1 and the row numbers E and E plus 1. So here I am denoting the row number. So this is row number E, this is row number E plus 1, and this right here is the column number, and this is column number E, and this is column number E plus 1. So these four elements, which are corresponding to either row number E or E plus 1 and column number E or E plus 1, are going to be non-zero, and all other elements in this particular matrix K are going to be 0, as we have just summarized over here. Similarly, the forcing vector Fa can be written as the summation over all elements ranging from element 1 all the way up to element n of FAE. Here, FAE again is the contribution of element E to the forcing vector F, and this is also going to be non-zero only if A is either equal to E or E plus 1, and for all other values of A, this is going to be 0. So if I plot Fe, then this is going to be a large n by 1 vector, but most of the entries of this vector are going to be 0. The only non-zero entries are going to be corresponding to row number E or row number E plus 1. Now, instead of maintaining this large matrix Ke, which is an n by n matrix, or this large forcing vector Fe, which is an n by n vector with mostly 0 entries, we choose to define an element stiffness matrix and an element forcing vector corresponding to just these non-zero entries, a 2 by 2 matrix for K and a 2 by 1 vector for Fe. So let's see what these element stiffness matrix and the element forcing vector look like. So we have the element stiffness matrix and element force vector. So the element stiffness matrix denoted by small k e is defined as KABE, which is a 2 by 2 matrix corresponding to these four non-zero entries. And here A and B refer to the local description of the element, and hence A and B take values of either 1 or 2. This can be defined as KABE is equal to integral over the domain of the element E of dNA by dx, dNB by dx, dx. Again, I'd like to highlight that here n small a and small b are the basis functions described in the local description. So here a and b are 1 and 2 since there are only two nodes associated with element E. Similarly, the element forcing vector small fe can be written as FAE, which again is a 2 by 1 vector, and the element FAE can be written as integral over the domain of element E NA F dx plus the boundary terms, which can be written as delta A1H for E equal to 1, 0 for most of the elements 2 all the way up till n plus n minus 1 and minus Ka2G for E equal to n. So this first term over here comes from this term over here, whereas this term over here comes from this term over here, related to the Dirichlet boundary condition and the Neumann boundary condition. So one thing I would like to clarify is that small ke refers to this 2 by 2 element stiffness matrix, whereas capital Ke is the global version of the stiffness matrix, which is the contribution of element E to the global stiffness matrix. So now, once we evaluate the element stiffness matrix small ke and the element forcing vector small fe for all elements, how do they then use them to assemble the global stiffness matrix? That's what we are going to discuss right now, the assembly process for the global stiffness matrix and the global force vector. So we know that this 2 by 2 element stiffness matrix is going to enter into row number E and E plus 1 and columns E and E plus 1 to form capital Ke, which is the contribution of element E to the global stiffness matrix. And the global stiffness matrix in turn is the summation of all of these Kes over all the elements by this relation over here. So knowing that, we can now write that the global stiffness matrix element KEE, which is row number E and column number E of the stiffness matrix K, basically this location over here, this location can be updated as its original value plus, apologies, K11E. So essentially, the element K11, which is the first row and first column of the element stiffness matrix, is going to be entering into KEE, this location over here, to form K capital E, which then is going to be summed up to get the total global stiffness matrix, and that's why we have this summation over here. Similarly, the element KE E plus 1, so row number E and column number E plus 1 in the global stiffness matrix is going to be updated as K12E from the element stiffness matrix. Similarly, Ke plus 1E, this particular element from the global stiffness matrix, is going to be updated as Ke plus 1E plus K21E. And finally, Ke plus 1 E plus 1, this particular element is going to be updated as Ke plus 1 E plus 1 plus K22E. So what these four relations here are telling us that the element stiffness matrix Ke, which is the 2 by 2 matrix, is essentially going to enter into this location over here to form K capital E, rows E and E plus 1, columns E and E plus 1, and that is going to be summed up to form the global stiffness matrix capital K. Similarly, the assembly process for the forcing vector can be written as element Fe from the global forcing vector is going to be updated by small f1e, whereas the element Fe plus 1 in the global forcing vector is going to be updated as small f2e. So more formally, we can define something called a location matrix, which is defined as follows. So more formally, to simplify these relations, we can define a location matrix, which is capital A equal to location matrix of small a, comma E. Here, small a is the local node number of a particular element E, which ranges from 1 to 2, since there are only two nodes associated with a particular element in the linear finite element method in 1D. E is the element number, which we know ranges from 1 all the way up to n, whereas capital A is the global node number, which we know ranges from 1 all the way up till n plus 1. So this relation, the location matrix, can be given by is equal to E if A is equal to 1 and is equal to E plus 1 if A is equal to 2. Now how did I get this? We know that if you consider element E, that element E has two local nodes, node number 1 and node number 2, whereas globally the two nodes are node number E and node number E plus 1. And hence node 1 is mapped to node E globally, whereas node 2, a local node number, is mapped to node number E plus 1 in terms of the global node numbers. So with this relation, the assembly process can be summarized as global stiffness matrix, row number, location matrix of E comma I, and column number, location matrix of E comma J. This element of the global stiffness matrix is updated as its original value, K of location matrix of E comma I, location matrix of E comma J, plus small k ij E. So the element in row number I and column number J of the element stiffness matrix, small ke, is going to be updating the element in row number location matrix of E comma I and location and column number location matrix of E comma J of the global stiffness matrix K. Similarly, for the forcing vector, the assembly process can be summarized as f of location matrix of E comma I is going to be updated by its original value, f of location matrix of E comma I plus f I E. So this is how, once we compute the element stiffness matrix small ke and the element force vector small fe, we can use them to assemble the global stiffness matrix capital K and the global force vector capital F. The last thing left to figure out is how do we actually compute the element stiffness matrix and the element force vector. Let's talk about that right now. Computation of the element stiffness matrix and the element force vector. So we know that the element stiffness matrix element KABE is given by integral over the domain of the element omega E dNA by dx dNB by dx. Now I'd like to remind you that since we are using a local description of the element, the local node numbers A and B take values A1 and 2 for element E. Now, since we are using a local description, let's change the variable from x to psi, the global variable x, to the local variable psi for element E. So using the change of variable rule, this can be written as integral over -1 to 1, because that's the domain in the local description, dNA by d psi, the local variable, d psi by dx, dNB by d psi, d psi by dx, dx by d psi, d psi. This can further be simplified as integral from -1 to 1 dNA by d psi, dNB by d, apologies, dNB by d psi, dx by d psi inverse d psi. Now, how do we evaluate the terms in this particular integral? So we know that in the local description, Na of psi is given by 1 minus psi by 2 for A equal to 1 and 1 plus psi by 2 for A equal to 2. So these are our basis functions in the local description. So this means that if we evaluate dNA by d psi, what we'll get is essentially minus half if A is 1 or plus half is A equal to 2. So this can be succinctly written as minus 1 raised to A divided by 2. Next, we want to evaluate what dx by d psi looks like. So for that, we recall that x of psi, the mapping from psi to x, can be written as summation A equal to 1 to 2 over both the nodes Na of psi x a e. So if we take the derivative of this, we get that dx by d psi is equal to summation a equal to 1 to 2 dna by d psi x a e, and we know that dna by d psi can be written as minus 1 raised to a by 2 x a e. This can be expanded as x2e minus x1e divided by 2, which is nothing but he by 2, where he is the width of element E. So now we substitute this relation dx by d psi equal to he by 2 and dna by d psi equal to minus a by 2, minus 1 raised to a by 2 into this integral, and what we can show is that implies kab for element E, which we knew was integral minus 1 to 1 dna by d psi dnb by d psi dx by d psi inverse d psi. This can be written as integral minus 1 to 1 minus 1 raised to a by 2 minus 1 raised to b by 2 2 by he d psi. When we evaluate this integral, we can summarize it as minus 1 raised to a plus b divided by he. So if you integrate over minus 1 to 1 d psi, we'll get 2. And so this 2 will be multiplied by 2. That gives 4 in the numerator. And we have 4 in the denominator. So that cancels out. And all we are left with is minus 1 raised to a plus b divided by he. So that is the expression for the element stiffness matrix for element E. In matrix form, this 2 by 2 matrix can be written as 1 over he comes out, and then each element is given by minus 1 raised to a plus b, which can be spelled out as 1, minus 1, minus 1, 1. So this right here is the expression for the element stiffness matrix for element E. Next, we need to compute the element forcing vector. So the element force vector FAE is given by integral over the domain of the element omega E Na times f of x dx, where f of x is our forcing vector, plus the boundary term, which can be written as delta A1 times h for E equal to 1, 0 for most of the elements ranging from 2 all the way up to n minus 1, and minus k A2E times g for E equal to n. Now for an arbitrary forcing vector f of x, this integral may not be possible to be evaluated analytically. Hence, in order to evaluate this integral, we choose to approximate f of x using our basis functions. So if you remember, our basis functions are also interpolation functions that can be used to interpolate the solution or any function in between the grid points. So if we evaluate the forcing function f of x at the grid points, we can then use the basis functions to approximate its value in between the grid points. So we approximate f of x as fh of x, which is an approximate version of f of x, is given by a linear combination of the basis functions. Here we use a local description, and so locally we have only two nodes b ranging from 1 to 2, fb times nb of x. Here fb is the value of f of x at the local node b equal to 1 and b equal to 2. With this approximation, we can now evaluate the first term in the forcing vector FAE. So the integral over the domain of the element omega e, Na times f dx, can be written as, firstly, we replace f of x by this approximation over here, and secondly, we change the variable from the global variable x to the local variable psi. When we do so, the domain of the integration is now from minus 1 to 1. We have the basis function Na times f of x can be written as summation b equal to 1 to 2 fb times nb, and dx can be written as dx by d psi using the change of variable rule. Now we know that dx by d psi is he by 2, and hence this can be written as integral minus 1 to 1 na times summation b equal to 1 to 2 fb times nb multiplied by he by 2 d psi. Now this can be simplified as, so we take the summation outside the integral and he by 2 is also pulled out. So this can be written as he by 2 summation b equal to 1 to 2 fb times integral minus 1 to 1 na of psi nb of psi d psi. So all that is left to do is to evaluate this particular integral. Now here, remember that Na of psi is given by 1 minus psi by 2 for a equal to 1 and 1 plus psi by 2 for a equal to 2. Now if you substitute the value of Na of psi over here and evaluate this integral for different values of a and b, then it is possible to show that this integral minus 1 to 1 Na nb d psi can be written as 1 plus delta AB by 3. So I leave it as an exercise for you, the viewers, to show this. Now when we substitute this into the equation, we can show that the integral Na times f dx over the domain omega e can be written as he over 2 times summation b equal to 1 to 2 fb times this integral over here, which we now know can be written as 1 plus delta AB divided by 3. So we have now showed that the element forcing factor FAE can be written as HE by 6 times summation B equal to 1 to 2 FB times 1 plus delta AB plus the boundary term, which we know is given by delta A1 times H for E equal to 1, 0 for E equal to 2 all the way up till N, and minus K A2E G for E equal to N. In matrix form, this can be written as Fe is equal to He by 6 times, so the elements are 1 plus delta AB, so they are given by 2, 1, 1, 2 times Fb, which is F1 and F2, the forcing vector, of course, plus the boundary terms. So this right here is the formula for the element forcing function FAE. And now we have all of the things that we need to solve the Poisson's equation in 1D using the finite element method. Using this relation over here and this relation over here, we can compute the element stiffness matrix and the element force vector for every element in our mesh. Once we do that, we can use the assembly process over here to assemble the global stiffness matrix capital K and the global force vector capital F. And once we do that, we can then solve the matrix equation KD equal to F to evaluate the unknown solution vector D. In the next lecture, I'll walk you through a computer program that does exactly that, and then we can get an hands-on experience of how to solve the Poisson's equation in 1D using the finite element method. Thank you for listening, and I hope you learned something.